Alright, hello Mr. Long, this is FRQ number 4. So part A asks us to draw and label a free body diagram showing all the forces that's acting on it. So for part A, the forces acting on it is Fg and then Fn, F and then Fk, and Fk, Fx, sorry, not Fx, Fk, friction. Alright, part B, using the data in the table, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value for acceleration ax, right? So we're given values of x and changes in t. So we would do our vertical axis as 2x and our horizontal axis as t squared, and we would get this from the displacement formula. X is equal to 1/2 at squared, and we just isolate for t. So we do that by multiplying 2 to the other side. So 2x is equal to at squared, and then we divide both sides by t squared. So it'd be 2x over t squared is equal to a. And this would match with the axes we have, where because the slope is y over x, and your vertical is y, and your horizontal is x, so it'd be 2x over t squared. And then I would use the remaining empty rows in the table to record the quantities. So this would be 2x m in terms of meters, and then this would be change in t squared in terms of second squared. So here it would be these values times 2, so 0.468, 0.986, 1.458, and 3.042, and then for t squared would be 0.04, 0.2601, 0.5476, and then 0.81, and then 1.69. Alright. Part C. It asks us to plot the data points for the quantities indicated in part B, and then scale and label. Okay. So I'll have my vertical and my horizontal. And then my vertical, as I dictated, would be 2x, which will be in terms of m. And then my horizontal would be t squared in terms, that would be units s squared. Right? And then for the intervals on the bottom, I would have it by 0.34. And then for the vertical axis, I'll have it going 0.62. Let me move this away. Let me graph the points. Here, and then here. And the last one all the way to the corner. And then I'll draw a straight line that best represents the data. Right. Part D, use a straight line calculated. Using the straight line, calculate an exponential value for acceleration ax. So I would do this by using my calculator. I would use the points I used here, and then I would do a linear regression. So I would do that right now. And here, 2, 0.468, 0.96, 0.458, 3.02. I think I gotta add something. Oh, 0.2601, 0.5476, 0.1, 1.69. Right. And then let's go. And here, it asks us for the linear regression, I would get the slope as 1.8. So it'll be 1.8 meters per second squared. And positive. All right. Part E, using Newton's second law, deriving the expression for the coefficient of kinetic friction, mu k, in terms of F, mg, data, and yeah, let me make a new page. Okay, E, part E. Okay, so, excuse me. You know that net force in the x direction is equal to max, and net force in the y direction is equal to 0. We also know that net force in the y direction is equal to Fn minus Fy minus Fg. And we know that Fy is going to be against Fn because in the diagram, F is being pointed downwards. So that means it's two forces being pushed down and one force being pushed up. So Fn has to be greater than them. So we can isolate, so we can equal the two net Fy equations together and then isolate for Fn. And we do that by adding Fy and Fg to the other side. Right. And we can expand Fy and Fg. Excuse me. Fy is going to be F sine theta, and Fg is going to be mg. And then we know that Fy is going to be sine theta because we know the angle is given here, and Fy is right here, and it's opposite. So it'd be opposite over hypotenuse. Okay. Going back to in the x direction, we know that Fx, net force in the x direction is also equal to Fx minus Fk, and then we equal the two net forces in the x direction equations together, so it'd be max is equal to Fx minus Fk. And here we would expand Fx and Fk, so the ma is equal to F cosine theta minus mu mu k fn, and then we get that by, because we know that mu k is equal to fk over fn, and we isolate for fk, we just multiply fn to the other side. And then here, we can replace fn with what we found earlier, so ma is equal to f cosine theta minus f sine theta plus mg. And here, I will move over f sine theta plus mg, that whole thing to the other side, and then I will move ma to the other side. So it'll be, for the ma, and it'll be f sine theta plus mg is equal to f cosine theta minus max. And here I would just divide, I forgot the mu here. Oopsies. uk and uk. Here I would just divide f sine theta plus mg to both sides. So the mu k is equal to f cosine theta minus max all over f sine theta plus mg, and that's the equation for mu k. Right, part F. Alright. If the applied force, so they give us values and we need to calculate the kinetic frictional force. Okay. So we've established that max is equal to fx minus fk, and then here to isolate for fk, I'll just move to the other side and subtract max to both sides. So it'll be fk is equal to fx minus max, and I'll expand fx and to f cosine theta, and it'll be minus max, and I'll just plug in values. So fk is equal to 12 times cosine 60 minus 2 times, or 1.8, because earlier we found the acceleration to be 1.8, and then fk is going to be equal to negative 2.1, or not 2.1, 2.4 n. Okay, g. Using the given values in part F, calculate the numerical value for the kinetic, or the coefficient of kinetic friction mu k. So earlier we found that mu k is equal to f cosine theta minus max all over f sine theta plus mg. Just plug in values. So mu k is equal to 12 cosine 60 minus 2 times 1.8 all over 12 sine 60 plus 2 times 9.8, and this would equal to 0.08. Alright. Part H. If the applied angle theta is decreased, what effect does it have on the acceleration ax of the block? Okay, so we know that fx is equal to ax, and that fx is equal to fx minus fk, and equal them each other, and then we'll expand fx, so and fk should be f cosine theta minus uk mg plus f sine theta, and then we just isolate for ax, so the ax is equal to f cosine theta minus mu k mg plus f sine theta all over m. Right. So it's asking for what happens if the angle is decreased. So if the angle is decreased, we know that this sign here, the value of the sign will go down, which would make this whole thing here, the minus mu k mg plus f sine theta go down. And then since theta would increase, we know that cosine increases with theta as theta increases, so this part will go up. So we know, so now you're going to be something bigger is going to be subtractive with something smaller, which means that ax would increase. So yeah, all right. Part I, okay. It asks us for the AT graph. So then, and then we use the time intervals that were given originally in the chart. So here I'll do kind of like this. And maybe meters per second squared. And then here, t times seconds. And here I'll just have the time, the intervals as the one given originally. 2, 0.51, 0.74, 0.90, and then 1.3. I mean, on the y-axis, I'll just have it going by like 0.5, 0.5, 1, 1.5, 2, and then 2.5. And then here, your acceleration is constant, so then the shape of it would just be 6, 7, 8, like this. This would be a straight line, a horizontal straight line, I should say. Okay. Sketch the shape of the velocity time graph. So I'll have my y-axis be velocity and my x-axis be time. T and then S. And here be V meters per second. And same thing as earlier, I have it just same time intervals. I'll just have the the vertical axis go by like 0.5 again. And then since you're accelerating constantly, your velocity would just be a linear slope. It would be like this. And it just asks for the shape of it, so you don't have to be too precise with the intervals and stuff. All right. Okay. Now it's asking for the position time graph. So use a time interval given the data table, and yeah. So here I would just do your y-axis as your position, and then I'll have it in terms of x. And then I'll have your x-axis be time, to be t, s, and here x, and then and then time intervals, it will be, I'll go by 0.27. And then for y-axis, I'll go by 0.4. Can be like this. Connecting them. Be like that kind of graphs. Yeah. So yeah, that was FIQ 4.